So let's start talking about a new concept. This idea of thermal physics. So thermal physics hinges on the idea of temperature, or at least it's related to temperature. Um, so what is temperature? Well, colloquially, right, we would say it's how hot or how cold something is. Um, I don't have a satisfactory like mathematical definition for you right now, but what I can say is temperature is that property of an object that when it's in contact with another object, so let's say this guy's cold and this guy's hot, you let them sit in thermal contact for a while. Sometime later, they will have the same temperature, right? So I don't know, we could call them both warm now, or tepid, right? But depending on their sizes, they may not each contain the same amount of thermal energy, right? Let's say we had a hot car and a quarter. Let's say you pulled a quarter out of the freezer and you put it in the hot car. They're going to come to the same temperature. Now they may both be hot temperature or cold temperature, but they're definitely not containing the same energy. So again, temperature. So we'd say this guy has a high T and this guy has a low T, and at some point later they have the same temperature. So clearly, temperature is an intrinsic property, meaning it doesn't change with the amount of stuff you have. Kind of like density, right? Mass is an extrinsic property. It depends on how much you have. But density, like mass density, is an intrinsic property. So it just depends on the material. Similar with this sort of thing. So let's talk about what you already know, right? How do you measure temperature? Well, you have a thermometer and it reads out something. So in the United States, we're used to temperatures in Fahrenheit, right? In fact, degrees Fahrenheit. And you're probably aware that temperature in Celsius is also a thing we can talk about, degrees Celsius. And if you've had a science course before, you probably are aware that you can convert between the two. So we have this equation that temperature in degrees Fahrenheit is 9/5 of the temperature in degrees Celsius. Fix that. Plus 32. So let me talk about a couple things here. That 32 is in Fahrenheit. Right? What does that 32 represent? It represents the difference in zero between these two. Right? So Celsius is defined between 0 and 100 for special points for water, right? 0 is where water freezes, 100 is where water boils. That's in Celsius. In Fahrenheit, those numbers are different, right? 32 degrees, positive 32 degrees is freezing for water for Fahrenheit, and 212 is boiling. So those don't seem like special numbers for water, and they're not. Fahrenheit's not defined for water. Fahrenheit is defined for, I think it's the triple point of a slurry of water and ice. You can Google that if you want to find that out. But again, these two things, this here. So the 32 is because their zeros are different. And the 9/5 is because their step sizes, so say degree sizes, are different. Right? And you can look at that and figure out which degree step is bigger. Or we can do this again and say for Fahrenheit, let's do this. We'll say freezing and boiling. Again, for water. Because again, those are things that we know. So for Fahrenheit, freezing is at 32 degrees and boiling is at 212 degrees. For Celsius, it's 0 and 100. Okay. Um, so you might look at that and say, well, then maybe Celsius makes more sense. Let me answer the question, or the thing that I'd posited a second ago, which was which one is a bigger step size? Well, we're talking about the same literal change in temperature, um, meaning from a freezing point to a boiling point for pure water. Fahrenheit is going almost 200, and Celsius is only going 100. So Celsius steps must be bigger for our reference. So if the temperature outside increases by 5 degrees Celsius, that's a bigger issue or a bigger change than 5 degrees Fahrenheit. But both of these scales have an issue for us. If we're going to relate this to energy, and we will eventually relate this to energy, then relating a negative temperature, which is totally valid for Fahrenheit and Celsius, to an energy, and energies cannot be, at least kinetic energies, cannot be negative. And that's what we're going to relate it to as motion eventually. We need a scale that is absolute, meaning 0 is the smallest number. All right, so for that we use Kelvin. All right, and for Kelvin, let's do this. For the Kelvin scale, 0 Kelvin is the lowest temperature. Period. You cannot get lower than 0 Kelvin. And we'll see that how we define it, or how we relate it to energy in a little while, or in a future video. But when something is at 0 Kelvin, it is literally not moving at all. Meaning 0 Kelvin is really hard to get to. All right, and the offset between Kelvin and Celsius is a simple subtraction or addition, depending on how you define it. So, again, a temperature in Celsius is a temperature in Kelvin minus 273.15. All right, and that 273.15, I suppose it's degrees, but it's also Kelvin. So make this note semantically about Kelvin. We don't say degrees Kelvin, we just say Kelvin. All right, it's just a semantics choice, right? Kind of like a language choice. So that means absolute 0. If the temperature in Celsius is 0, well, not absolute 0. So absolute 0 is minus 273.15 Celsius. And often I drop the 0.15 because 3 sig figs is typically enough. So we could say for freezing water, you could put a 0 in here equals the freezing temperature in Kelvin minus 273. So clearly the freezing temperature for water is 273.15 Kelvin. All right. And then the boiling point must be 373.15 Kelvin. Room temperature is pretty close to 300 Kelvin, right? Because room temperature is like 20 Celsius. Notice again that this offset is strictly additive. So that means that the step size for Kelvin and the step size for Celsius are the same. That does something really cool for us. That means if I have a delta T is the same in both Kelvin and degrees Celsius. All right, it's because it's just an offset, right? So if I increase the temperature of something by 20 degrees Celsius, I have also increased its temperature by 20 Kelvin, right? So if I have a delta T of positive 20 degrees Celsius, or really we would say Celsius degrees, and that's because we're not talking about an absolute temperature anymore. It's a relative temperature. Then I've also increased it by 20 Kelvin. Right? It would not be okay to subtract 273 from that. It wouldn't make any sense. Okay, so we'll see lots more examples with that in it. In fact, let's do one right now. So there's another concept here that I want to introduce in this same video, which is thermal expansion. I can do better than that. Thermal expansion. which is to say, when things get warm, they tend to expand. When things get cold, they tend to shrink. There are some exceptions to this. I'll talk about that maybe in lecture. So, what are we talking about? Well, the idea is this, that let's say we have a metal bar. This is a good place to start. Say you have a metal bar, and you heat that metal bar up. So if I don't know, let's say add some delta T. That's a terrible way to put that, but I'm going to say it that way anyway. When you do that, it tends to expand. All right. Think if you've ever seen joints in a let's just Google it. If you've ever seen joints in a bridge, there. Let's see what we get. Yeah. All right. These joints are to allow for thermal expansion of the road. That's not a very good one because it's kind of unclear. But here you can see how there's some space there, right? And so in the summer when things are hot, those can grow together, and in the winter when they're cold, they pull apart. If you don't put that in there, you get cracks in the pavement. The other thing you can see is thermal expansion of railroad tracks. Yeah, that's great. Let's look for more of them, please. There, so you can see lots of these thermal expansion of railroad tracks. Why does this happen? If you butt the ties up together too close, when they try to expand, there's no way for them to go, and they will bend. And this happens violently. I suggest you look for a video of this. So you put joints in. So you see this one right here. There's a joint there that allows for a little bit of expansion. Okay, so we model this, but we model it empirically. Let me show you what I mean. So here's my initial length. So length initial. And this little bit at the end is the increase. So that's a delta length. All right, and so we can see, well, I expect delta L to be related to delta T. And in fact, if you measure this, if you plot delta L versus delta T, you get a straight line. I'm not going to plot that. I'm just going to say, so delta L is directly proportional to delta T. It's also proportional to the initial length, right? So if you start with something longer, it experiences a much bigger delta L. So length initial, it's related to delta T directly, and then a constant of proportionality that we'll call alpha. All right, and alpha here is the coefficient of thermal expansion. Coefficient of, and specifically this would be linear thermal expansion. So alpha, L initial, delta T. And alpha is something you would measure experimentally. So again, I said you could measure delta L as a function of delta T. You can plot that. You see it's a straight line. The slope of that line is going to be related to L initial and alpha. So you can get alpha out of that. In fact, let's look at some alphas. So if we go to the lecture handout, try to be in here. It's not. There it is. So if we look at the lecture handout, at the bottom of the second page, here's a list of several of these coefficients of linear expansion. You see something like 10 to the minus 6 is pretty common, right? So we don't see this it's not a noticeable effect visually unless something spectacular happens, like the railroad tracks have to bend off because miles of them are bumping into each other. But you can see that they're different for different things. I want to point out that concrete and steel are pretty close together, and that's allowed us to reinforce concrete with steel rebar, because concrete's pretty brittle. So steel allows a little more structural integrity, while still allowing for the use of concrete, which is cheaper. All right. Otherwise, you could just make everything out of steel. So that means when steel enforced concrete expands, the steel and the concrete expand about the same, and they contract about the same. Okay, so let's do an example real quick. So this is example number 1. The length of a steel beam increases by 0.74 millimeters when its temperature is raised from 22 to 35 degrees Celsius. What is the length of the beam at 22 degrees Celsius? Okay, so let's draw a picture. There's my initial length. Again, it's getting a little longer. There's my delta L. Delta L is given to me as 0.74 millimeters. Clearly, I'm going to have to correct that or convert that. What else do I have? I have a T initial, which is 22 degrees Celsius, and a T final, which is 35 degrees Celsius. Okay? And the question is, what is L initial? And I'm told that this is steel. And we just saw for steel, alpha was something like 11 times 10 to the minus 3. Sorry, 10 to the minus 6. And the unit on that is inverse Kelvin. And that's because we're relating a length to a length times a temperature change, right? So it's not meters per, it's just per Kelvin to make the units work out correctly. Okay, so we can solve this. We can plug into the equation. I've got delta L equals L initial times alpha. Let's put the alpha first. Alpha times L initial times delta T. And remember, delta T means T final minus T initial. Okay, so delta L. Delta L I know is given to me. It was, I'm going to move over a little bit. 0.74 times 10 to the minus 3 meters equals 11 times 10 to the minus 6 times the initial length, which is what I'm looking for, times T final minus T initial. Now, I told you that the SI unit for temperature is Kelvin. But I also told you that if you have a delta, it doesn't matter. Let me prove that to you. So delta T equals T final minus T initial. And if I'm being careful, I need to convert both of these. That means I need to add 273 to both, right? So T final is 35 plus 273 minus 22 plus 273, right? So if you do that math, what do you get? 13, right? Because 35 plus 273 minus 22, you get 13. Prove it to yourself by plugging it in. So that was Kelvin minus Kelvin. But what do I get if I take 35 minus 22? It's 13, right? Because embedded in this conversion here, this difference is 273 minus 273. The conversion factors cancel out. It's kind of like when we take the ratio of two things in something that's not SI units. As long as the units are the same, the conversion factors go away. So this is one of those cases. So I can just leave this in Celsius and say 35 degrees Celsius minus 22 degrees Celsius. Again, we need to be careful about that, but it does work out for delta T's. So if I do this math for the initial length, let's do that quickly. So 0.74 E minus 3 divided by 11 E minus 6 divided by 13. I get 5.1 meters. Okay. So we will see in the future how this applies to volume. Actually, let me just say it right now. So how does this apply to volume? Well, if this happens from one direction, it will generally happen for all three. So we have another equation for volume, which is delta V equals beta V initial delta T. And you probably saw here, it was earlier in the same. I have these expressions for volumes as well. So the volumetric coefficient of expansion is in this right-hand column. We have those for both aluminum for linear and for volume. But here I also have it for lots of liquids, right? Acetone, benzene, ethyl alcohol. So we can play this game with both linear expansion and volumetric expansion. So there's your introduction to thermal physics.